Howdy, all. I'm John. I'm an environmental sustainability major. And so the project I'm talking about today is my capstone, which is an aeroponic food growing system. Now, those are systems that grow plants and other foods, except they use nutrient solution instead of soil to provide the food for the plants themselves. Sorry. There we go. All right. So I chose this project because it has a really interesting origin story. In the spring semester of 22, NASA and the Canadian Space Agency, their Canadian counterparts, set up this deep space food challenge in which they wanted ideas for food systems that would sustain their astronauts on long missions, like if they're going to Mars or something like that. And I'm not sure how it came to you, Bob, but we got a chance to set up a team and work on the project, which was pretty freaking awesome. So some background on hydroponic food systems themselves. There are 7 major types, and we are using the aeroponic, which is in the upper left-hand corner. Again, all these use nutrient solutions, thus they all have a reservoir of what looks like water. And aeroponic systems use sprayers to actually mist the nutrient solution to the seeds or the roots of the plant. That's what makes them unique. And the thing about these systems is they're a really great engineering project because you can use a whole bunch of varieties or variants and you can scale them up and down. And so there's a lot of pros to these types of systems in terms of sustainability. So some of the pros are that they use about, depending on who you ask, they use only about 2% to maybe 10 of the water that traditional agriculture uses. So they're really water efficient and nutrient efficient. Plus, because you can scale them up and down, they're pretty space efficient, and what you can grow is really, really healthy. Plus, most systems are used indoors, so you can grow food all year round, which is also pretty nice. The only drawback is once you get the systems that are a lot larger, like industrial sized, you incur a lot of costs in terms of energy and space. For example, the pump, you need energy to pump the nutrient solution to the seeds, or you need lights to, grow the plants. So those are costs that you incur when you get really big systems. And so again, what this means is that due to scalability, you can provide food for like an entire state or an entire region. For example, up top here, we have an industrial sized hydroponic system that happens to be in Qatar, an arid place, which doesn't have a lot of water. And because these systems are water efficient, that's really good for them. That's probably growing millions of plants at one time that could provide food for the area. Whereas down at the bottom here, we have a system that's growing maybe 6 plants that's very DIY that probably is good for maybe a salad or two. And yes, sorry, that was a bad joke. Now because these systems have limits on their size, they're probably never going to be able to compete with big or traditional agriculture in terms of how much they produce overall, but they can certainly fill in the gaps where those systems fail to meet, like food deserts or actual deserts where there's less water. And so important factors to note when you're building a hydroponic system, most of which are familiar to people who grow plants. You have lighting conditions, you have the pH of your water, you have the air and water temperature. The one thing that's kind of unique to hydroponic systems is electroconductivity, which is basically the measure of ions in the nutrient solution, which basically is a proxy for how much nutrient concentration there is. So some plants like a higher concentration, some plants like a lower concentration, but electroconductivity, otherwise known as EC, is really important in that situation. And so on the left here, we have a chart of the PC ranges and the elements at which, or the elements for the PCs, sorry. At certain pHs, certain elements become more soluble and usable for plants. And so you want to keep your pH for your hydroponic nutrient solution within a pH of 5.5 to about 7. And then on the right, you can see all the plants and the food that gets grown, and you can see there's a variety of pH and EC. Some range from about 0.5 EC to about 5.5. That's a very wide gap in terms of what type of concentration the plants like in their food. So in building our aeroponic system, we started out with the reservoir, which holds the nutrient solution itself. It's a 55-gallon tote. You can buy them at Home Depot or Lowe's. We drilled some holes in the top. And then so we used the pump to send nutrient solution through the pipe, through the sprayer head to the net pot, which is what holds the seeds. So that's the method which we use to transfer nutrient solution directly to the seed. And there on the left, you can see our aeroponic system as it is now. On the right, we actually had a first iteration which did not work because sometimes that happens in science. And so at first, when you don't succeed, you got to try again. And we had worked on it long enough that it was worth definitely building a second set. Now, for our experimental setup, we were going to test 3 different electroconductivity levels on broccoli microgreens, microgreens being basically a baby version of the large plant. And we were going to test ECs of 0, which is pure water, of 0.8 and 1.6, which are still pretty low ECs for a plant. And our hypothesis was that the 0.8 EC would give us the biggest growth of microgreens. This is just a chart of the example of all the conditions that we monitored. And so originally we were going to use coding to automate the pump and the lights. That didn't work because the first iteration didn't work. So we were still going to use Python code, which is here for data analysis at the end of our project. We were going to use the Kruskal-Wallis test to determine differences or significances in differences between the outcomes. So as our results so far, at the top, you can see what a harvest looks like of about 80 microgreen seeds. It's not very much. It's only a couple grams. And then the chart is our results chart so far. We're about 2/3 of the way through. And then if you notice on the left, that's one of our, that's the net pots in the reservoir tote lid. Unfortunately, not all of the pots got watered due to some engineering flaws because it's just the way the system was designed didn't quite work the way we wanted it to again. So yeah, sometimes the pots got water, sometimes they didn't, and sometimes they had growth, and also sometimes they didn't. So the final steps for this project would be finishing collecting the data analysis, and of course, writing the final report for the capstone, and then in the future, perhaps engineering a better system. And before I run out of time, I would like to thank Dr. Wolf-Pescher and Professor Sam Dean, who I believe are on here. Thank you, guys. And then Dr. Giovanni Vincenti for helping us and his AITC students with the coding of the first iteration of the project. So thank you.
Can I ask the first one? I am curious about what failed in the first iteration.
So it's the way when you pump water vertically, it starts out at a certain pressure at one level, but it gets weaker as it goes up. So we tried to send water up and it went like about 2/3 of the way up. So not all the net pots got water. So like the spray was really weak. It was well contained. We had the code down. The design looked pretty cool. Dr. Pescher and I spent time building it and all, but again, it just didn't work in the end because basically the pump wasn't strong enough at that point.
Thank you. This is such a cool project. So you talked a little bit about being able to be like small and then also take up a large amount of space. Do you think at this point or at any point this will become a viable option for people to like supplement or replace like backyard gardens? And if so, and if so, how large can the plants grow in these?
So I've seen plants grow as big as tomatoes. I've actually grown tomatoes hydroponically. So I've gotten the stems to get up to about 6 or 8 feet. Now, in terms of, yeah, they're nice. Now, in terms of replacing backyard gardens at the moment, that 2-tower system that I showed as our first iteration, that all cost about $750 to make. So the startup costs right now are a little prohibitive, and it has a niche, but it's not quite being as fulfilled. Urban agriculture is also getting in there too, but I certainly feel like it'll fill in the gap that big agriculture and traditional soil agriculture cannot fill. Like in Baltimore, I think we have 24% of the people who don't have access to healthy food. So that would definitely be a place where it could fill in.
Thank you so much.